Hey everyone, ready for some mind-blowing cosmology?
Always up for a cosmic adventure.
Excellent, because today we're diving into a topic that's got scientists scratching their heads.
Oh yeah, this was a real head scratcher.
The universe, as we know it, is expanding, but it's doing it faster than anyone expected.
Way faster, like stepping on the gas in a cosmic car.
Perfect analogy. We've got some fascinating research from NASA and the ESA about this, and let me tell you, it's a game changer.
Yeah, we might have to rethink some of our fundamental understandings about the cosmos here.
So let's start with the basics. Just how much faster is this cosmic expansion anyway?
Okay, so according to data from NASA's Hubble Space Telescope, we're looking at a whopping 9% faster than all our previous predictions.
9%. Seriously, I mean, that's not just a little off. That's a huge difference.
You got it. And on a cosmic scale, that 9% is a monumental discrepancy.
So how did they even figure this out? You can't exactly measure the universe with a ruler, right?
No, definitely not a simple ruler situation. They're using something called the cosmic distance ladder.
Cosmic distance ladder. Okay, now you have to explain that one.
All right, imagine you're trying to measure the distance across a huge field, but your tape measure isn't long enough. What do?
Well, I guess I'd use markers at specific distances to help calculate the total length.
Bingo. Astronomers do something similar with special types of stars called Cepheid variables. They're like cosmic mile markers spread across the vastness of space.
Cepheid variables. Remind me, what makes these stars so special?
They pulsate with a predictable brightness. Think of it like a cosmic heartbeat. The dimmer they appear to us, the further away they are.
Uh-huh. So by observing these cosmic heartbeats, we can figure out how far away these stars are.
Exactly. Hubble has been watching 70 of these Cepheids in a nearby galaxy called the Large Magellanic Cloud. It's about 162,000 light years away.
Wow, 162,000 light years. And by tracking these Cepheids, Hubble was able to calculate this new, faster expansion rate.
Precisely. They combined Hubble's observations with data from another project called the Arakaria project.
Okay, so the cosmic distance ladder, these Cepheids,
Right.
it's all starting to click. But you mentioned something earlier called Hubble tension. What's that all about?
Yes. The plot thickens. See, this new expansion rate from Hubble is causing quite a stir because it completely clashes with another set of measurements we have of the early universe.
You mean the data from the ESA's Planck satellite, the one that mapped the cosmic microwave background?
You got it. That afterglow radiation from the Big Bang, like a baby picture of the universe.
Hi.
Planck gave us a pretty solid prediction of how fast the universe should be expanding today.
And that prediction is slower than what Hubble is telling us now.
Significantly slower. That's the tension saying. Two different methods of measuring the universe's expansion leading to two conflicting answers.
So it's like we have two different cosmic speedometers and they're giving us different readings.
And the chances of this being a fluke? Astronomically slim, like 1 in 100,000.
1 in 100,000. Wow, that's not just a margin of error. That's a
Yeah.
cosmic conundrum.
You could say that again. Means something's not quite right with our current understanding.
Hold on. So you're saying our whole cosmological model, the framework we use to explain how the universe evolved, could be wrong?
Whoa, let's not jump to wrong just yet.
Yeah.
It's more like we're missing a piece of the puzzle. Our model's based on a ton of evidence, including the Planck data, but this new Hubble data.
It throws a wrench in the works.
Exactly. Like we were following a cosmic recipe and suddenly realized one of the ingredients was measured completely wrong.
So it's not that our understanding is entirely wrong, but rather incomplete, like a story with a missing chapter.
A missing chapter with some pretty mind-blowing implications. And that's where things start to get really interesting.
Okay, hold on a sec before we dive into the interesting part.
Going somewhere.
I think we need to back up just a bit. I'm still a little fuzzy on the cosmic distance ladder and these Cepheid variables.
Right, good point.
Yeah.
It's pretty crucial to grasp that before we jump into the deeper implications.
Okay, let's break down this cosmic distance ladder a bit more. How does it actually work? How do these Cepheid variables help us measure such immense distances?
All right, picture this. All right, so we're talking about this cosmic distance ladder, right? Think of it like building a bridge across a giant canyon. You can't just throw one long plank and hope for the best.
Right, you need supports.
Exactly. You build it step by step, supporting each section with the one before it.
Okay, I see where you're going with this. So these Cepheid variables, those are like the first strong supports in this bridge.
Perfect analogy.
Yeah.
We know Cepheids have this special relationship between how bright they are and how fast they pulsate.
Right, like their own little cosmic heartbeat.
Exactly. So by watching how quickly a Cepheid brightens and dims, we can actually figure out its true luminosity, like how much light it's actually putting out.
Okay, so we know how bright it actually is, and then we compare that to how bright it looks to us here on Earth.
Exactly. And the dimmer it appears, the farther away it must be. It's a pretty simple concept, right?
Yeah, I get that. So that gives us the distance to that first rung on our cosmic ladder. Then what?
Then we use that distance to calibrate other distance indicators. Things like certain types of supernovae.
Supernovae, those exploding stars.
Yep. Some of them always reach the same peak brightness.
So if we see one of those supernovae in a galaxy that also has a Cepheid variable, we can compare their brightnesses
And figure out how far away that supernova and its galaxy must be.
and since supernovae are way brighter than Cepheids, we can see them even farther away.
Bingo. It's like extending our cosmic ladder even further out into the universe.
Wow, so it's a whole chain reaction of measurement?
Exactly. Each one building on the last. Pretty amazing, right?
It is. But let's bring it back to this Hubble tension for a second. How does this distance ladder play into all of that?
Well, think about it. If the distances we're measuring using this ladder are even a tiny bit off, it throws off everything built on top of it.
Ah, I see. So like if that first support beam of your bridge was messed up, the whole thing could be unstable.
Exactly. So this 9% faster expansion rate that Hubble measured, it could mean there's something fundamentally off with our distance measurements.
You mean like those first few rungs of the cosmic ladder might not be as accurate as we thought?
It's definitely a possibility, and that's why this whole thing is sending shockwaves to the scientific community. We're having to double-check everything.
Man, my brain hurts. This is some heavy stuff.
I know, right? But it's also super exciting.
Oh, totally. It feels like we're right on the edge of some major discoveries. So what are some of the explanations for this discrepancy? Could things like dark matter or dark energy be playing a role?
Those are the prime suspects. We know they exist, but we don't really understand what they are or how they work.
So is it possible they're messing with our measurements somehow, making it seem like the universe is expanding faster than it really is?
It's definitely on the table.
Eh.
Some theories say that dark energy, stuff that's supposed to be driving the universe's expansion, might be getting stronger over time.
Oh, wow. Like a cosmic gas pedal that's being pressed down harder.
Yeah, that's a good way to put it. Or maybe there's some weird interaction going on between dark matter and dark energy that we haven't figured out yet.
Okay, now this is where my head really starts to spin, but it's fascinating.
It is. And some physicists are considering even more radical ideas, like modified gravity.
Modified gravity, as in Einstein's theory of general relativity, might need a little update?
It's not impossible. Or, get this, there might even be extra dimensions beyond the 3 spatial dimensions and 1 time dimension that we're used to.
Wait, hold on. Extra dimensions, like parallel universes and stuff?
Well, some theories do suggest that. It's mind-blowing, but some physicists take it seriously.
Okay, so we've got dark matter, dark energy, modified gravity, extra dimensions. This is a lot to take in.
Right. It's a whole lot cosmic mystery.
But it's so exciting to think about. This Hubble tension could lead to some groundbreaking discoveries.
Absolutely. This could be a turning point in cosmology. It shows us we still have a lot to learn about the universe.
You know, thinking about all this, it's kind of humbling how much we don't know.
Definitely. Every discovery just seems to open up more questions.
But that's what makes it so cool, right? Cosmology is all about exploration and discovery. It never gets old.
Exactly. And the coolest part is we're all a part of it. Whether you're a scientist or just someone who likes looking at the stars, we're all connected to this incredible universe.
That's a great point. And to everyone listening out there, all this cosmic talk is making your head spin. Don't worry.
Yeah, don't get lost in the technical stuff.
Right. The point is to appreciate the wonder and the mystery of it all.
Let it remind you how much there is out there to explore.
And who knows what incredible discoveries are still to come. Maybe one day we'll crack the code of this Hubble tension and unlock even deeper secrets of the universe.
We can only hope.
Okay, well, that's a pretty awesome thought to ponder.
Before we move on, though, there's one more thing about this Hubble tension that I think we need to address.
Oh, lay it on me. What else is there?
We've talked about the evidence, the theories, the scientists, but what does all this mean for the future? Like, the really big picture future?
Okay, now you've got my attention. What does this Hubble tension tell us about the ultimate fate of the universe?
That is the million-dollar question, and the one we'll try to tackle in the last part of our deep dive. Stick around.
Okay, so we're back and ready to tackle the big question. What does this Hubble tension tell us about the future of the universe?
Well, it's a question that's been on the minds of cosmologists forever, And this new discovery, it's adding a whole new layer to it.
So give it to me straight. What are the possible scenarios we're looking at here?
Okay, so one possibility is something called the Big Freeze, right? If dark energy keeps dominating the universe's expansion, galaxies are just going to drift further and further apart.
And eventually,
Eventually, they become isolated islands in a massive cold and empty cosmos.
that's kind of depressing. Everything just spreading out into nothingness. Are there any other, more uplifting possibilities?
Well, there's some theories out there that say dark energy might not be constant. It could actually change over time.
Change how?
Potentially, it could even reverse its effect and cause the universe to start contracting.
Wait, so instead of expanding forever, the universe could start shrinking.
Exactly.
Yeah.
But eventually, gravity would win the battle against dark energy, pulling everything back together.
Into like a single point.
Right, a super dense point, a big crunch, as some call it.
Whoa, that's wild. So it's either a big freeze or a big crunch. Are there any other crazy scenarios out there?
There are. Some physicists have even proposed a big rip, where dark energy becomes so powerful, it rips everything apart.
Rips everything apart.
Yeah, like not just galaxies and stars, but atoms themselves.
Okay, that one's a little scary.
Yeah, it's pretty dramatic, but it's important to remember these are all just theoretical possibilities, right?
Right, but still mind-blowing to think about.
Absolutely. And that's why we need more research. We've got to figure out what dark energy is really doing and how it's shaping the universe's future.
So the fate of the universe is still a big mystery.
A big, beautiful mystery.
Yeah.
And this Hubble tension, it's just making things even more interesting.
I've got to say, through all of this, it's kind of humbling how much we still don't know.
Oh, totally. But that's the beauty of cosmology, right?
It's a never-ending journey of exploration and discovery.
Exactly. And we're all part of it.
So to everyone listening out there, if you're feeling a little overwhelmed by all this cosmic talk, that's okay. Don't get bogged down in the details.
Just let your imagination run wild.
Embrace the wonder and the mystery, because who knows what incredible discoveries lie ahead.
Maybe one day we'll solve the puzzle of this Hubble tension and unlock some of the universe's deepest secrets.
That's a great note to end on. A huge thanks to you for joining us on this cosmic deep dive. It's been a wild ride.
It's always a pleasure to talk about the mysteries of the universe.
And to our listeners, keep those minds curious and never stop exploring. We'll catch you next time on The Deep Dive.